Our primary focus right now dealing with systems has been on linear systems, and specifically ones that are homogeneous. And they are of this form here. So where we recall that this is the vector of derivatives for our two differential equations, dx dt and dy dt. Then inside of the y vector, this guy contains the undifferentiated variables, and so when we put this together, we get ax plus by and cx plus dy, and so we can see dx dt is ax plus by and dy dt is the bottom row. Now let's extend this a little bit, and let's suppose that not only do we have the ay component, remember this matrix is what we call A, but we also have this other vector here that contains some functions of time. And I've labeled those, and these aren't anything formal, just to stand for non-homogeneous, n. And then there's n for n sub x of t and n sub y of t. So these are some functions, and we're going to refer to this matrix as B. Right? It's technically a vector, but we'll use a matrix, a capital matrix letter for it. For some well-behaved functions, n sub x and n sub y. Okay, we'll come back to this. What does well-behaved even mean? I mean, does it mean like it does its homework on time? What does it mean, right? So we'll come back to that in just a moment. So to solve this, it turns out we don't actually need any new tools. We just need to revisit existing ones. The extended linearity principle we've used to solve non-homogeneous equations. And the process of the extended linearity principle extends to this, no pun intended. First, we solve just the homogeneous version, and we call this the homogeneous reduction. So solving for that will give us y sub h. Okay, in other words, it'll give us a vector of solution. So inside of here, we'll have x of t and specifically x sub h and y sub h. So this is exactly the same thing. We're just going to have two functions in there. And the means by which we solve, of course, will be eigenvalues and eigenvectors. Next, what we need to do, just like with the extended linearity principle, we need to find one particular solution to the non-homogeneous equation where B is just going to have that, is going to be the label for nx and ny. Okay, that solution that we get out of here will give us y sub p, and then the general solution is the sum of the homogeneous and the particular. Okay, so what do we mean by well-behaved? Well, in this situation, it's similar to when we faced it with non-systems. So this was the common guesses form that we used, if you recall, and it looks very similar, except our A and B are just matrices here, or vectors rather. And so these are kind of the well-behaved, where you're a constant, or you're a linear, or you're a quadratic, but starting to combine these gets significantly more complicated. And so ideally, we're dealing with pretty clean functions that don't mix and match. Polynomials aren't ever a problem. It's just when we get into like the sum of a polynomial and an exponential, things can get a little fishy, a little more difficult. So let's take a look at an example. So in this case, the system of equations that we're looking at is 2x plus 0y plus 5. That's going to be for dx dt. So the 5 is the non-homogeneous term. And non-homogeneous, remember, means anything that doesn't involve, any term that doesn't involve the dependent variable. Well, dx dt, 2x, and 0y all involve the dependent variables. And then the plus 5, it does not contain x or y in any way, shape, or form. And so the second equation just corresponds to the second row. Okay, so to solve this, we would first begin with the homogeneous reduction. I'll just label that AR, and that's going to amount to finding the solution for the matrix 2, 0, 4, 3. So I'm going to need my lambda 1 and my lambda 2. Those actually come out to 2 and 3. By the way, notice if you have a 0 above the diagonal, which goes from top left to bottom right, doesn't apply when it goes the other way, top left to bottom right, then, and there's a 0 above that diagonal, then your eigenvalues are the diagonal elements. Now, there's my V1 and V2, which you can calculate using any calculator. And now we want to put this all together. So we know that we have two real eigenvalues. So our solution is going to be y equals k1 e to the lambda 1, so 2t, times v1, to the vector 0, 1, plus k2 e to the 3t, e to the lambda 2t, times v2, negative 1, 4. Now we'll leave it like this. You could calculate x of t and y of t. X of t would be the correspond to the top row, y of t would be the bottom row, and so x of t would be 0 k1 e to the 2t, or just 0 plus negative k2 e to the 3t, and little y would be 1 k1 e to the 2t plus 4 k2 e to the 3t. Now, that's all we really need to do for the homogeneous reduction. Now for the non-homogeneous. Okay, so how do we attack this original non-homogeneous problem here? Well, in much the same way, we formulate a guess. Okay, so if I was just given one equation, my guess would be a constant, right? Because I want to make sure that the derivative of x is equal to 2 times x plus 0 times y plus 5. So I have to be able to get a constant out of there. And so I'm going to guess my y sub p vector to be something like this. For the first equation, I look at the non-homogeneous term, I see it's a constant. So I'm going to guess a constant function for little x sub h. The non-homogeneous for the y is also a constant, and so I'm going to guess another constant and little a and little b. So x sub h equals a, y sub h equals b. So these are both constant functions. And now what do? Well, now what I need is, if this is x, I'm going to need the derivative of this function, and the derivative of y sub p dt will be 0, 0. Okay, so now I get to plug all this stuff back in. So up here in our equation, I'll just write this out one more time. Dx dt equals 2x plus 0y plus 5. And for my second, I have 4x plus 3y plus 4. That's d little y dt. Okay, so if I dump this into the system, derivatives are both 0. So here's my derivative. And so that corresponds to this vector. So I'll have 0 and 0. 2 times x, well, x, we're guessing a constant function, so it'll be 2a. Y, we're guessing the constant function b, so it'll be plus 0b plus 5. And for the bottom equation, we'll have 4 times our guess for x, which is a, and plus 3 times the guess for our y, which is b. Now, we're doing the exact same thing that we did when we were dealing with non-systems, but we only had one equation into which we had to insert our guess. Now we have x sub h, y sub h, dxh dt, that's the derivative, dt, a little sloppy there, dyh dt would be this guy right here. And so all we're doing is we're replacing those values there. Now we have a system of equations to solve. Turns out this one's pretty easy, so we don't need to use an equation solver. We have 0 equals 2a plus 5. And the second equation we have is 0 equals 4a plus 3b. Now you can solve this system using technology, but I can just subtract 5 over and divide by 2, and a comes out to negative 2.5. And now I can plug it in over here, and I get 0 equals 4 times negative 2.5, which will give me negative 10 plus 3b. And you see, it's just real quick to do this. b will equal 10 thirds. And so what's my final solution? Well, my y sub h, therefore, is equal to a and b. So a will be negative 2.5 and b will be 10 thirds. I think I'm just going to go ahead and leave these both as fractions, just so I don't have to round the 10 thirds. It's not really a good idea to use mixed fractions and decimals. So I'm going to go ahead and list this as negative 5 halves and 10 thirds. And so my general solution will be y equals y homogeneous plus y particular. What was y homogeneous? Well, that was the k1 e to the lambda 1 t v1, 0, 1, plus k2 e to the 3t, that was lambda 2, negative 1, 4. Let's see how we're doing so far. Make sure I remembered that correctly. Okay, good. And finally, then we'll have plus the y, sorry, this was y particular over here, not y homogeneous. And y particular will be negative 5 halves and 10 thirds. And so there you go. You have x of t would be the top row, y of t would be the bottom row. Remember, that's all the capital Y stands for. And so now you could actually write the equation for each of these. For instance, little x of t will be 0 k1 e to the 2t, so that term will disappear, and we'll get negative k2 e to the 3t minus 5 halves. For little y of t, we will get 1 k1 e to the 2t plus 4k2 e to the 3t plus 10 thirds. And there is our solution. And now if we were given initial conditions, so now solve for k1, k2. Don't solve for k1 and k2 after you found the homogeneous, because when you add in these terms, it's going to change what happens when you plug in 0 for time, right? The negative 5 halves will, and the 10 thirds will now contribute. And so, of course, that would result in a different k1 and k2. But this is a basic example. We'll take a look at a more complex one in the next video.